Deve stare un po' più accurato. Sono ha detto che però non ha pubblicato niente, allora là è una vuoi perché c'è qualcosa che effettivamente tanto importante che fanno fatto domanda per e quando si tratta di industria però sempre la comunità
So welcome everybody. This is a very interesting event. So today we will celebrate the Day of Light, and probably you know, but the Day of Light is an event that is let's say instituted by the UNESCO since 2018, and the special day of May 16 is due to the first laser functioning event in 16 May of 1960. So we now today celebrate this very relevant invention that you know is has a lot of application in many fields, in a lot of application that we have today, but of course is based on very basic science, very fundamental knowledge of nature. So it's really a perfect example of let's say the merging between fundamental science and application every day. So with this, I leave the floor to Paolo Villoresi, that is a representative of the University of Padova in the Photonic 21, that is a European consortium of photonics stakeholder, and then to Nicole to present who is organizing this event, that is the Pulse SPIE and Optical chapter. So please, Paolo, and thank you for your presence here.
Thank you, Pino. Good afternoon, everyone. Indeed, the Day of Light is day to celebrate. I'm just back from Brussels, where there was the annual meeting of Photonic 21. It is important also to understand a bit the context. In Europe, there was already about 20 years ago the vision of putting together the interest in photonics in several aspects. That goes from surgery, so looking at the brain or having the laser to cut it, to lightning, to telecommunication, to energy, to quantum, to science. And this essentially was, say, framed in a context that for each framework program is provided to the Commission, to European Commission, as, say, a list of topics, emerging needs for the continents to support. And the Commission then take these suggestions, and this becomes the calls to which the research group like ours may apply to. Okay? So there is the need of having a vision on all the different aspects of photonics. And I'm delighted to be part of this say team, because you really realize that there are a lot of different directions. You are working on some subject which, of course, to you is interesting, is relevant, but I suggest you to look around, because there are many other aspects in which maybe your own tools, your own say techniques are used or can be used or are developed in a way that can be useful for you. Okay, so these photonic things seen in general has a lot of possibility, a lot of resources. Okay, the photonics itself as a say economic economic aspect is growing despite other despite the situation and much more than other sectors, is growing for more than 5% per year. And in the time from here to the end of the decade, the overall global value of photonics will overtake the €1 trillion. Okay, so it's a lot globally. Okay, it's a lot. The point is that often you don't see it as a team, as a like I don't know, artificial intelligence, which is a thing that encompass, but it is used in many other sub disciplines. And I would like to congratulate with the organizer today that provides speakers, and we are happy to welcome also Roberto that made it to Padova, so difficult. That say brings you the view from different aspects, so to provide an example of how diverse can be the subject, but at the end is all using light with smart ideas. So I will give to the organizer a slide with essentially the link to the actually information you can have about this Photonics 21 and the correlated say growth and importance. With this, thank you very much, and Nicole, back to you.
Technical issues. Okay, thank you, Pino. Thank you, Paolo, for the introduction. Thank you all for being here. Today I'm here. Today we are here to celebrate the International Day of Light, and I will now I'm representing the Pulse Student Chapter that organized the event. So first of all, what is Pulse? Maybe it will work, maybe not. Oh no, it's here. Sorry. It doesn't work anymore. Okay, I will do like this. So what is Pulse? What is the student chapter? Pulse is the Padova University Light Scientists and Engineers. We are a group of students who promote events in science and light and photonics and much more. And we are students, we are PhD students, but we can also include master students and bachelor students. So if you are interested, please come and let us know. We work within the University of Padova. And we are able to promote these events thanks to the financial support from Optica and SPIE, which are explained here. They are two societies that are dedicated to the promotion in a worldwide situation of all topics that are in the field of advancing optics, photonics, and all kind of technology that are based on the advanced light science. Which kind of events we promote? In the last years, we have promoted many kind of events. We have also helped in 2022 with the Quantum Internet Hackathon. Here we can see some photos also of the event. Last year, we also did the International Day of Light, and it was a successful event. And recently, we also have participated to the Q-Hackathon at the Quantum Communication School. And here we have Pino and Federico Berra, that was one of the presidents last year with the winner of the poster session. And recently, we also collaborate with the Q-Hackathon at the School of Quantum Cryptography. And here also another very nice photo of us. And maybe some of you have been to our lab tour that happened last month, and where we present some of our laboratories and some of our activities. And about today we will have 3 amazing talks with Dr. Luigi Vesce from the University of Tor Vergata, Dr. Alfonso Nardi from the ETH Zurich, and we will also have Prof. Roberto Zellame from the IFN CNR. I would like to dedicate this small slide to all the people who helped with the organization of the event. In particular, there are 3 main groups that help, that are the photonics and electromagnetics group, the optoelectronics, the ACME group, and the quantum future group. And here there are some photos of our meetings that we have done in the last months to organize the event. And I would like to thank you all for the time and effort you dedicated to the event. So we can start. And the first speaker we will have is Dr. Luigi Vesce, who is a researcher in the field of electronics and photovoltaics at the Department of Electronic Engineering. And Dr. Vesce received his master's in engineering and a PhD degree in the telecommunication engineering at the University of Tor Vergata. And he has held various positions throughout his career. He has been a research fellow in the Institute of Telecommunications of Aveiro, and he has also been a telecommunication design and engineer in Tallinn and an engineer collaborator with Dyers. He has been a senior researcher and a team manager with Dye Power Consortium and an engineering collaborator with INGEN. He is currently a senior researcher at CHOSE, which is the Center for Hybrid and Organic Solar Cells, and he is also lecturing in electronics for the Electronics Engineering Master course. Today, he will enlighten us with his talk about perovskite solar cells, upscaling routes by large area and printing technique. Welcome. Here. Now this works.
Okay, good afternoon. Thanks for the nice introduction, and thanks for the organizer for inviting me at this event. I am Luigi Vesce. I work as a researcher at the Center for Hybrid and Organic Solar Energy. That is a research group at the Department of Electronic Engineering in Tor Vergata University. And today we talk about perovskite solar cell upscaling routes by large area printing techniques. Briefly, I will introduce my group, so CHOSE group and labs, and then I will talk about the perovskite solar technology and how we work on the upscaling of the technology from cells, from lab cells to mini and to sub-modules. And so we will discuss about the technological, environmental, and cost assessment of the perovskite technology. Okay. So the center, CHOSE, is located in the Tor Vergata University campus. The center was founded in 2006, and I was there from the very beginning. The main objectives are the printed electronics, the research and development on organic, dye-sensitized, and perovskite photovoltaics. So our aim is to work on the device design, on the scaling up, and so on the technology transfer to industry. So we aim to be a sort of cross-link between the basic research and industrialization. This also by founding some spin-off, some startup, also offering collaboration and counseling to new companies. So the photovoltaics is our main input, but this permits us to work on several fields as energy storage, printable thermoelectrics, LED, and light efficiency. So in this way, we can find new applications, materials, architectures, and processes. I want to briefly introduce you the Agenda 2030, just to more showing you which are our main topics and our targets. So in September 2015, the international leaders met at the United Nations and approved this agenda. The agenda is composed by 17 goals that are the Sustainable Development Goals related to the global development, to human well-being, to the environment. So each country has to contribute to these goals according to what the country can do, and they are not independent. We can say that our work is mostly related to SDG number 7 and number 9, that is related on the first one on low cost, reliable, sustainable, and new energy systems for everyone, and the second one to the industry that should be sustainable and innovative. And then, yes, we have also some effect in other sustainable development goals, for example, the climate action, but just to focus on these two. Okay, here I want, so we are a group that works on photovoltaics. We were born as working on sensitized solar cell. And then during the last decade, we moved to the perovskite field because of this really amazing growing up of the efficiency that in just in one decade the perovskite solar cell technology got. So in just one decade, the perovskite went from 9% efficiency, that was the very first devices fabricated, to more than 26% now on small area cell. This is thanks to the heritage from the printed electronics, for example, and also to the all the knowledge from dye sensitized solar cell, for example, because most of the mainly some materials and most of the processes are also heredited from these technologies. Here are also some key elements of the perovskite solar cell technology that also testify the success of this technology. Just a summary: so the very low exciton binding energy, the possibility to have a high absorption coefficients, the possibility to work on flexible devices, to realize semi-transparent or transparent devices that can work also in indoor condition. This opened the field to plenty of applications. So as I said, the light harvesting, so indoor, or also on flexible the devices like the consumer electronics. Also there are some activities related to the agrivoltaic and so on. Perovskite solar cell. So the perovskite for the photovoltaic is typically composed by an organic and inorganic cation like cesium, methylammonium, or from aluminium. Then you have a metallic cation that is typically or lead iodide or tin, and then you have a trihalide anion according to the band alignment, to the application that you have to work on. The typical NIP structure of a perovskite solar cell is composed by an ETL, that is an electron transporting layer that helps to avoid some shunting paths. Then you have in the middle the perovskite absorber, and then you have the HTM to collect the holes, and the top metal electrode. The working mechanism is maybe I think that as all of you knows about a solar cell. So after the light hits the device, you have an exciton photo generation and the dissociation. Then you have the selective injection at the HTM and the ETM interfaces, thanks to the band alignment, and then the injection in the positive and negative contacts. But here, today we want to discuss about the technology aspect of the perovskite solar cell, and the real exploitation at market level of this technology can be realized only if small lab scale cell are transferred to module devices. So there is a classification typically according to NRL, and also to some reputed journals, where you can classify the device according to the size. So a lab scale cell is something when your active area is less than 1 centimeter square. That is as the picture that you can see here. So these cells are, yes, the glass is 2.5 by 2.5, but the active area is less than 1 centimeter square. For example, here is 0.09 centimeter square. Here is 1 centimeter square, 0.5 centimeter square. So here these are just devices for testing the materials in the lab. But then you have to do something that is more close to a real device, so it's something that you can apply, that you can install in somewhere. And so there is the classification about the module. The module is the interconnection in series, for example, of different cells. The classification is related to the mini module, for example, that is when the size is less than 200 centimeters square, and sub-module, where the size is more than 200 centimeters square. Then there is also a further classification, large area module and so on, but it's something real bigger. So I mean, I said about the interconnection of different cells. Here is a schematic of the interconnection. On the left here is the stack of a single cell. Okay, that is a typical when you want to optimize the technology to find the best. So the best trade-off between each material. Here we have, for example, the glass that is covered by a transparent conductive oxide. But as I said, we can also do everything on flexible plastic substrate, but here is related to glass. Then you have tin oxide as ETL. Then you have the perovskite absorber, the PAE, that is a passivation layer, but then we will discuss about some details of this material. And then the spirometal, that is an organic material that works as HTM. At the end, you have the counter electrode, that in this case is the gold. Here, the interconnection that generally one can be adopted is a series interconnection. And there is the classification related to the dead area, to the active area, and so on. So the dead area is related to the interconnection, because at the very end, if you deposit each layer by layer, you have just one cell. So if you want a module, you have to design from the beginning the device. And here there is this classical scheme that is the P1, P2, P3. The P1 is the first step that you are going to do, that is related to isolate the conductive substrate according to the number of cells that you want. Then you have the P2, that is something that you do after the deposition of the full stack, except for the counter electrode. This is to guarantee the interconnection with the counter electrode. So with the P2, we remove the full stack in order that with the subsequent gold the position, we can guarantee the series interconnection. Then we will discuss about the issue behind this process. Then you have the P3, because after the evaporation of the gold, you have one electrode, but you have to separate according to the cells. That's why we have a dead area width that is related to a portion of the device that we need, but is not active. So at the very end is not generating some current. And then you have the single cell active area width. In this case, is the width, but think about this stack in a 3D way. So this is the width and this is the height. But now we are working on this. We are discussing about this. One should optimize the interconnection, such as the dead area width is as much smaller as possible, because it's something that doesn't generate any current. And then you have the single cell active area width. So at the very end, I anticipate some issues. So when in the upscaling process, there are some issue. That one is the front contact sheet resistance that is related to the conductive substrate. That's why, to mitigate this, to try to face this, one have to choose a low sheet resistance substrate. Generally, we work with substrate with 7 or 10 ohm square. And then optimize the cell series connection, the cell with optimization. That's why when I need a big substrate, I don't fabricate just one cell to face this issue of the front contact sheet resistance. Then you have the issue related to the interconnection of the area, so we already discussed. So here we have to narrowing the interconnection and separation lines. So it's a matter of the optimization of the laser process and the layer in homogeneity that is related to the deposition of each layer. Maybe it can be simple to deposit on a very small substrate, but it can be completely different. You are going to deposit on a very big substrate. Here you have to work on the coating technique, material composition, and the deposition environment. Everything is important. So if you want to fabricate a PV device, but PV device, a perovskite PV device, I mean a module, so something like in the picture that you can see, that size is about 300 centimeters square. The process should achieve some basic requirements, that is the device performance, the stability of the device, and the process should be reliable and with a high throughput. And also the manufacturing process should be low cost as much as possible and eco-friendly. These are typical deposition technique about thin films. The spin coating cannot be considered a scalable deposition technique because of the size limitation, because of the material wasting, because you put more material that we need for the process. And so generally one should work on different process as the blade coating process or slow die coating that are quite similar. You have this bar that deposit the material on the substrate, and you have to control the meniscus, that is the gap between the lip and the substrate, and the slow die is similar, the working mechanism, but only difference is that you have a continuous supplying of material inside the head coater. This is good for very big substrate. And then you have also the inkjet printing in some case. Today we will talk mainly about blade coating and the slow die coating. Here I would like to show the first step of the scaling up. So to scale up from small area cell to something that is a module but is not such big. In this case the size is 32 centimeters square. We work on the machine that you can see in this picture, that is designed together with a startup from our group. This machine can be both a slow die coater or a blade coater. Is equipped with different facilities. For example, we have an air knife to pre-dry the layer. then we can control the temperature of the plate. We have some fun after. This is the syringe applicator for the slow dye and so on. So as you can see from the picture on upper left, you can see that the full process is in ambient air. This means that as generally one prefer to work with the perovskite in glow box with the nitrogen environment, here we work in ambient air. This means that yes, the ambient is controlled with the fume hood and so on, but we have oxygen, and we have also some moisture that is controlled in some way, about 30–40% humidity, sometimes also less. But we are not in the glow box. So it's something more similar to a process manufacturing. Here you have the full step. So everything is by scalable coating technique at the very end, because we have the spray coating of the compact TiO2, the blading of the TiO2, blading of the perovskite or the HTM, and the 3 laser process that I have already presented to you. The process is a one-step process. This means that first we deposit the precursor solution with the blade coater, and then we have some preliminary drying after this step, but the layer is still wet. And to complete the perovskite conversion and growing up, we use the anti-solvent technique. So we put a solvent, in this case is isopropanol, that can washing out the solvent that we need for the formulation of the perovskite. In this case is the DMSO and DMF. Then you have a step of annealing. Here is some picture of the homogeneity assessment. These pictures are from a work that we did in collaboration with TUM, working on the machine learning of this process. And so here, yes, we got a lot of characterization and so on, but here it's more easy to understand 3 pictures. So on your left, you can see the picture of an optimized position. Then in the middle, to show you how the single process parameter can play a role in the position of a good perovskite, and also the other layer. So in the middle, you can see if the deposition of the perovskite, for example, is too slow. Here we notice that the solvent is trapped in the film. You have not the conversion of the perovskite. And on your right, you can see if for example, the perovskite deposition is too fast, so you cannot have a complete perovskite growing. Then another homogeneity assessment is to, for example, divide the substrate in different spots, in different parts. And here we measure, for example, the absorbance and the photoluminescence in different points to see if we have a big difference. And also we check the morphology according to the blade direction, because sometimes if the process is not optimized, you can have some difference at the beginning and the end of the deposition. But here you can see that the perovskite grains are quite homogeneous if we take a picture from the beginning or the end of the deposition. And also we realized an electrical homogeneity assessment. So we realized the different cells in different portion of the substrate. So here this is not a module, but in a sides of a module we realize different cells in different parts of the substrate. In this way we can compare if the performance are with not so much big error. Here you have 16 small area cells that are this yellow part. Each cell is 0.09 centimeters square. We compare this with the process in by spin coating. That is should be the best case, no? So spin coating in a glow box, so in a nitrogen environment. You can see that the champion efficiency is quite similar, about 17%. So this means that the blade coating process is comparable to the best performing case. And the good point is the statistics. As you can see, you have a very small error if you use a scalable technique, because you have a more homogeneous layer and with the less defects and so on. Then here is the to prepare the model, you have to work on the laser patterning. We already introduced the P1, P2, P3. So as you can see, the P1, you ablate the part of the TCO according to the number of the cells. The P3, the counter electrode. The most tricky is the P2, because with the P2, you have to remove the full stack without damaging the TCO, because if you damage the TCO, for you it will be impossible to realize the series interconnection. We optimize this by different technique. For example, if we know the thickness of the stack, the etching depth, so the gap of the trench should be comparable to the thickness stack, because we are removing all the stack, and also we conduct some SEM EDX analysis to see if in the trench there are still the element related to the perovskite. We can see that in the P2 trench we remove the lead, the iodine, the carbon, the oxygen. So all the perovskite elements are removed, and just a small signal related to the tin, but is related to the tin conductive oxide. Here you have the module. You have 5 modules for each deposition technique. You can see that in this case, the performance of the bladed modules are better with respect to the performance of the spin coated one, because of the homogeneity that we get in the deposition of the perovskite. And so it's better both the champion efficiency and the statistics. Then we make some preliminary aging test in light soaking. Yes, in light soaking at MPPT. Here you can see that the T80 is not so different between the two techniques. 750 hours for the blade coating technique and about 780 hours for the spin coating technique. But it's also important to see the behavior of the trend after the T80. So the spin coating is completely going down because the defects will start to play a role, and the blade coating substrate are going to be almost stable under some percentage. We perform also the homogeneity assessment, this in collaboration with Fraunhofer ISE, by comparing the PL switching and so the photoluminescence and the electroluminescence of the module. Thanks to the photoluminescence, we can see the charge extraction ability of the module, and thanks to the electroluminescence, we can see if we have some cracked cells, some defects, some failed interconnection, and so on. On your left, you can see the case about the blade, and on your right, the spin. About the PL, there is we start to have some different. You can see some dark spots here, not so much, but here, yes. So you can see some dark spots about the spin coating case. Here you can see as the charge extraction is not uniform between the different cells, and in the blade coating case is much better. About the electroluminescence, you can see better maybe it's the most important characterization. You can see how all the cells are different between the different in the spin coating case, and how are quite similar in the case of the blade coating. I said that we want to see, okay, we want an efficient, stable device, but we want to keep an eye to the environmental impact of what we are doing. The life cycle assessment is a good method to test the environmental impact of each product that you have around. The life cycle assessment helps to realize the label that you have also in your washing machine or TV and so on. And so this approach takes into account the full cycle of a product. That's why the method is related from cradle to grave. Here in collaboration with the University of Siena, first we compare different deposition technique by spin coating, blade coating, spin coating plus press, it's another method, and blade coating in the glove box. The input data from our side are this column, and this other column are from literature. In red are the most different steps between the procedure, the different procedures. So in the first case, they deposit the perovskite by spin coating. Here we deposit the perovskite by blade coating with the process that I already showed to you. Here is a spin coating with the method that they apply a press on top, and then the blade coating in the glove box. With this method in input, we have all the materials, energy data of all the steps. So the process is divided in different steps. Each step has materials input, energy input. So we have to take into account how much energy we consume, how much material we use, and then you have the output that is as shown here. So this is the the eco profile of the fabrication processes. According to with the blue, you have the blade coating in glove box. For example, in orange, you have the blade coating in ambient air. You can see that the blade coating in glove box is the most impacting process. If we take into account 100% impact for the worst case as a reference. This is because of the anti-solvent that they use, this de-ethylator, that is really not good material from an environment point of view, and also the electricity consumption of a glove box. That's why also that if you want something that can be like a pilot line or similar, it's better to work outside the glove box. The lowest impact, as we expect, is by blade coating. This because you have a low electricity consumption, low material waste, and also use less harmful materials. Is not in this graph because here is an accumulated graph, but the gold deposition is the most critical manufacturing step, because you have to use gold, you have to use a high vacuum process by evaporation. Then at the end we will see how we can remove the gold. But we want to further upscale. Now we see how we go from the mini module to sub module. So something that is 300, so 10 times bigger than the module that we have seen before. And this chart is as the chart I showed at the beginning of the presentation, but related to the module. These are all champion module certified module efficiency. If we stay in the sub-module frame, there are some attempts, but the manufacturing process is still in the glove box. But also with a huge drop if we compare to smaller devices. It's also difficult to find something in the literature. There is plenty of examples about mini modules, but about some modules, it's really hard, because if some first, for example, Toshiba and Panasonic showed something with efficiency about 16%, still in glove box, it's hard to find deep details also because they are industry, so they want to not publish all the details. There is this paper in Sure Energy with this efficiency of 15.3% on 200 centimeters square. Here is still in the, but it's still in globe box, but they use some scalable techniques, so the slow die coating technique. In this case, you have a very huge drop with respect to the lab scale cell. For example, with respect to lab scale cell, they show about 36% efficiency drop, and about the mini model 25%. So still a huge difference. This is our process for the sub module. About the perovskite is quite similar to the previous one. Now in the next slides, I will show the details about more or less each step and how we reach to this process. But again, the full process is in ambient air. Everything is by scalable coating technique. Now we introduce the slow die coating because of the sites, and now we see how we reach this. So first we try to deposit on such big substrate just by blade. So we deposit both the perovskite and the anti-solvent by blade. We got this efficiency about less than 8%, and it's easy to understand also from this picture. This is a good perovskite, this is a bad perovskite, just to inform you that because of the blade coating technique, we cannot guarantee a steady state meniscus. Meniscus is the gap between the blade and the substrate for the full substrate. So the substrate is too big, and we cannot control this by blade. And so we use the slow die coater for the anti-solvent step, and we can improve the efficiency till 12.6%. And also in the absorbance spectra, you can see the better uniformity. For example, the red is related to the hybrid meniscus coating. I mean, hybrid is blade plus slow die, and blade is the black one. So you have some difference because of this behavior. And also the higher absorbance in the hybrid meniscus coating is related to the bigger grain sites that you have in the same image. And then if we have such big subset, we have to pay attention to the defects that at the very end you have mostly at the interface between the layer, and this happen mainly because when you are going to transfer deposition techniques optimized for mini module to bigger module. So we deposit this passivation layer, the phenylethyl ammonium iodide, that also we use in the past, but by spin coating method. Now we deposit also this layer by the slow die coating method. And by XRD, we can see this peak at 4.7 degrees that testify the presence of the PAE. And thanks to this, we can suppress the non-radiative recombination losses and improve the VOC, as you can see from the blue line, and with a maximum efficiency of 13.7%. But we want more. We want to fully remove at our best the problem that we can have in this process, and we work on the DMSO sticking. The DMSO is one of the solvents that you use when you prepare the perovskite solution. Recently, also by some of our experience in the lab, we face this issue, so that during the perovskite formation, some DMSO can be trapped. So in between the substrate and the perovskite layer, and then when the DMSO escapes, you have some voids formation. These voids are the starting point of the degradation of the system, and so we decide to use a some high vapor pressure solvent in order to fast dry the DMSO solvent. And so we use this acetone nitride solvent in order to have a uniform evaporation rate. We can also notice that we improved the position repeatability of the layer. Also, you can see that from the SEM you have a larger grain if you add this acetone nitride that justify the good formation growing of the perovskite. In this case, we got 14.5% efficiency, so further improving the results. At the end, we put all together this improvement in one module, and then first we check the electroluminescence. Here you can see that you have some small defects. There is some resistance still you have some variation, but not so huge. You have some inhomogeneities, okay, but there is not a huge thickness variation, not any shunt defects that you cannot see oneself, for example. And this is good for the measurement. There is no contribution outside the aperture area. The aperture area is the area of the full module from the first cell to the end of the last cell, also take into account the interconnection area. There is no contribution outside, so this means that what you are measuring is something trustable. You have no any contribution and extra contribution. Then we check the morphology, still again in some different points to see if we have some big difference. Then the champion device got an efficiency of 16.1%. And if we compare with our lab scale cell, we have a drop just about 9% and no drop with respect to the mini module. So this means that we are replicating the results of the mini module on a bigger substrate. Here is the stabilized efficiency of 15.5% with a short light soaking, and also the stability according to the ISO's D1 test. ISO's D1 test is a test of shelf life test. So we are not applying temperature or light. We are just keeping the substrate in a drawer somewhere in the ambient environment. And here we have some decrease, about 10% after 3,000 hours. Again, we did the life cycle assessment of this device, and we compared the results with the mini module. So about the environmental impact, that is this column, we can see that by upscaling to the sub-module, we had a better usage of the materials and of the instruments, and we also increased the throughput. But in both cases, we can see that still the gold evaporation is the most impactful process that you have to eliminate. There is also some preliminary consideration about the manufacturing cost. So we can reduce in some way the costs if we upscaling, because there is a better usage of the resources, and in both cases the materials, as the materials have the big impact on the cost level. This cost analysis doesn't take into account the labor cost and so on. But the life cycle assessment helps to also to start thinking in the eco design way. So this means that when you are designing a process, you start to think about the impact that this process can have on the environment. Here is the comparison of the two processes, so mini module and sub module. And the life cycle assessment testify that the choice that we did are good also from a technology point of view. For example, in the mini module, we still use the spray coating at high temperature, the blade coating, and the sintering at high temperature. And these are two processes. So the high temperature process is something that you have not to do if you want to have a low impact process. So we remove these two processes and we move to a low temperature process for the TL. So because they are, but also it's good from a technology point of view, because in the case of big module, high temperature processes are not good because you can start to fail your devices. You can start to make the deformation of device and so on. So it's good also from this point of view. And in fact, we show the mitigation in all the environmental categories of the process. This is there are some reliable output, because here is an example where who can do the life cycle assessment meets who fabricated the devices, and so you have some primary data. You have not something that is extrapolated from literature and you have to simulate and to think something. They are real data. Okay, but we want to further improve the efficiency of our model, and so we start to change the perovskite composition. Essentially, we work on this FAPI perovskite. That is a very narrow band gap perovskite, and we deposit the perovskite in as the process as which I showed you before, with this double step process. We got this very good efficiency, about approaching 21% on small area cell, on 0.5 centimeter square active area, and that is also testified by the integrated current. And then we realize some modules with the maximum efficiency of 18.5%, some mini module. Okay, but from the life cycle assessment, something is missing, no? We saw that the gold, we have still gold in our stock. We have still gold, so we have to remove gold. And one option in the perovskite field that is also from the dyes inside solar cell is to substitute the metal counterelectrode with the carbon counterelectrode. You have two options mainly. That is the high temperature or low temperature concept. In the high temperature concept, you deposit your material except for the perovskite, because you have to treat the carbon layer at high temperature, so I mean 500 degrees. After the deposition, after the annealing of the carbon layer, you have the infiltration of the perovskite in the carbon porous system. But this is still a high impact process, because you have again a high temperature process. That is, it's not as such impact as the gold evaporation, but you have still this high temperature process. So we have removed the high temperature, now we have one more. So, and another concept is the low temperature carbon. In this concept, you can deposit the carbon after the perovskite. So you have not to infiltrate the perovskite, so you can also control better the crystallization of the perovskite. You can also integrate some HTL. This is compatible with the flexible substrate and with the roll-to-roll process, so to also to speed up the production line and so on. And so our efforts are mostly involved in the low temperature concept. There are some motivation in general to substitute also, as I anticipated, the gold counterelectrode, because with the metallic electrode you have some ion diffusion towards the perovskite, as we discussed this morning, and also you have some light metal oxidation. The gold has a very low hydrophobicity, so this means that you have more impact with respect to the moisture, and also you can avoid to use organic HTL that has very poor thermal stability. So in the last years, this concept, the scientific community believes that the carbon counter electrode can, in such a way, meets all the needs for the technology. So to be efficient, stable, with low cost and sustainable. Here is our some preliminary experiment that we are doing, and the process is as you more or less already have seen. Don't consider P1 and P2 that is ready to model. We will explain later. In this case, we remove the gold. We optimize some HTM, that is, in this case, is this inorganic CIS HTM in collaboration with the Sharif University of Technology in Iran, that is robust to the carbon solvent, because yes, we are depositing carbon now, such as a ink, a paste, so we have some solvent inside. So you need something that is robust also to this solvent. And also the low temperature carbon thermal treatment is not an issue. Low temperature, I mean 120 degrees. Is also such most stable according to these results, thanks to Sharif University that shared with me. And also this is the best efficiency that now we got, that is 15% on 0.5 centimeter square. And with the process that you can see here. So here we can also claim that is really footprinted at a low temperature. We have no evaporation, so it's everything that we can do with scalable, really scalable technique. And here I show you the module. It's a preliminary module, so the dead area width is most big now, also the P2. So this is the P2, and this is the P3. But in this case, we remove one laser process. So we have this laser process and this one, but not the P3 process, because we can deposit this carbon ink by screen printer. So by screen printer means that you have a screen on which you have the layout that you need, the number of cells that you need, the interconnection area that you need, so we can profit of the high throughput of this method. These are the first module that we realized. The efficiency is 11.4%. And if we compare with something present in literature by screen, we are almost in the right way. Here is such a little bit higher, but they use blade coating for the carbon, so means that they put a tape by hand on the module, deposit carbon, and then remove the tape. So it's something that yes, you can do in your lab, but if you want to present that something that is scalable and transfer to the industry is not so good. Just to conclude, I show briefly how the glow box module by hybrid meniscus coating. This should be the highest efficiency ever reported in such condition. We have very low scaling up losses. And also we investigated the technological, environmental, and manufacturing cost benefits. These can be such compatible with the same industrial scenario. To conclude, I would like to acknowledge the main project that is funding us, and all the people involved in this activity. My supervisor, Professor Aldo Di Carro, and the PhD student Elena, Maurizio, Afez, and Kartikeyan. Thank you very much.
Do you have any questions? I have more like a curiosity. I've Ricardo, you talk about the flexible perovskites. I wanted to ask how are we about flexible perovskites now? Are we going to see them in the market anytime soon?
So thanks for the question. So the flexible perovskite are really interesting, no? Because you have a very such a huge application. The main drawbacks of this technology is because of the substrates, because the substrate in some way has some it's weak with respect to the permeation of the moisture, for example. So that's why this kind of technology people are going to show, and something is already visible, but not with organic, not with perovskite, but with organic with the pure organic photovoltaics, with some indoor application. So with some electronics, some small apparatus. Yes, as you said, it's really good because also you can profit for a high throughput process because you use the roll-to-roll process, for example. But you have to face this issue about the moisture and also about the very high resistance of the layer. That is something 10 times more than the glass. So the glass, you have something that is 7-10 ohms square. With the flexible, we are about 30-40 ohms square. And also you have some drawbacks related to the laser process because you are putting some such high power not on glass, but something that is plastic that you can eat very easily.
Thank you again.
Thank you.
Thank you, Dr. Vesce. Now we will do 5 minutes break. So let's meet back here in 5 minutes. Thank you all. Okay.